Hello. Oh, hello, hello. Good afternoon, Daniel. Good to see you. Good after. Oh, okay, here we go. All right, all right. Good afternoon, Daniel, who is waiting patiently as ever. Good afternoon, Nikaya, who is here enthusiastically as ever. Okay, I'm not going to make a comment on each person. Good afternoon, Yun. Good afternoon, Jenna. Good afternoon, Jerry. Hi, Ashley. Good afternoon, Sam. Good afternoon, Alyssa. Good afternoon, Amarani. Good afternoon, Darina. All right, all right. Awesome, awesome. Hello, hello. Excellent, excellent. Okay, I'm in a good mood because I'm actually outside, as you can tell, so I can wear a mask. Oh, wait, more people coming. Um, but the cost of being outside is that my internet, everything, all connections are super unstable. Professor psychologies are super unstable. So we might suffer a technological meltdown at some point, but if we don't, we'll suffer a psychological meltdown, and if we don't, we'll be good. All right, we're going to start. All right, people are still coming in. Actually, it is right on time. Okay. Um, 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 you'll see that I just changed the date on a number of things. I changed the date on all the October 1st game things to November 1st, just to make it clear that none of those are late and none of those have time sensitivity. They're like one-offs. Um, and I changed the date on homework 3 to give you another week to do it because we're still talking about homework 1 and 2. So there's nothing new assigned. Just homework 3 has been changed to next week or something like that. Oh, sorry. Hello, Jennifer. Good to see you. Um, oh, okay. Um, 1 second, sorry. So we're all still in the process of catching up with ourselves. Most of you have gotten, well, I think all of you have gotten homework 1 back. I think most of you have gotten homework 2 back. There's still like 4 or 5 people that totally handed in homework 2, or at least some portion of it, but haven't gotten it back yet. I apologize. It's like 4 or 5 people. It's not personal, it's alphabetical. And it'll come. All right, today we're finally moving on with well, today we're probing the end of homework 1, which is really, it's taken us this long to get to sort of like the meat of something here. And the end of homework 1 actually led us to face, for the first time in our lives, or the first time in our formal lives, to face a differential equation. It is not expected that we've done differential equations before. It was not expected that Isaac Newton or Robert Hooke, I think his first name was Robert Hooke, had faced differential equations before, when the physics just brought them to that mathematical reality. That's the same thing with us. We are going to invent and discover and experiment and think through, just like they did. Math is something that is figured out and people accept it because it makes sense. Um, so, uh, and then it just becomes a tool that's easier to use once you don't have to actually invent it. But the actual nature of scientific investigation and scientific research is to have to actually make tools as we go and then use them, which is ultimately, I think, more satisfying and also leads to a better ability to use the tools. Anyway, so the point is that the question we had at the end, the question that we had at the end of homework 1 was the seemingly simple, okay, at time equals 1 second, where's this mass going to be? It was literally, you name the time, can we name the position? Nothing could be more fundamental or central in physics, but that doesn't necessarily mean that nothing could be easier in physics. Sometimes it's very simple, but not easy, as is the case here. Hold on, keep going. So we're asking for any given time in the middle of an oscillating system, such as this mass on the spring, for any given moment in time, can we determine the position? So what we're really asking ourselves is, can we find position as a function of time, given these specific physical constraints. Constraints which are common, natural, realistic, reasonable, and sort of simple to express, but not necessarily constraints that are easy to navigate. So what happened right at the end of last class is we for most of the last class, I tried to explain what it really means to be a differential equation and how a differential equation is different from just any old equation that has a derivative in it, or at least that not all equations that have derivatives in them are differential equations. And we just started to solve the differential equation that we have here. The differential equation we have here is what's on the front page here, d2x dt squared equals negative k over mx. We are going to solve it. Oh, good afternoon, Luna. Great to see you. And thank you for saying so. We're going to solve that differential equation. We're going to get the solution or a solution that's actually written here at the bottom of the page. So that's the answer we're going for. I'm not at all suggesting that we've already gotten that answer. We have not. I am saying that you might be familiar from the interwebs or something. You might have seen that answer before, or also just so you know, I'm going to try to establish that that's the answer. But just notice, like we're going to try to find that answer today, the answer that's written at the bottom of the page here. But don't, and you can write it down if you want or not, because we're going to derive it. But I just want you to notice, without overthinking it or worrying about it or stressing about it, just notice the form of it. It's got x on the left side, the dependent variable, isolated by itself on the left side, equals some constant times some function of some constant times the independent variable. I just want you to see that answer, there's no reason you should assume that answer is right. There's no reason you should understand necessarily that the answer, I mean, like maybe you do, that's great. But I'm not saying here, duh, obviously that's the answer. What I'm just saying is that like x equals 1/2 at squared plus v naught t plus x naught, this has the form of an x, it has the form of x as a function of t. That's the type of function we're looking for, x as a function of t. X equals 1/2 at squared has the right form, but it's not the right answer because it has an a in it. It assumes that there is some value of acceleration which is constant. Our whole premise here is that the acceleration is not constant. So we're looking for some kind of thing that is x related in some way to t, but some kind of x as a function of t that satisfies this differential equation. This differential equation, which I might add, and then I'm going to look in the chat, and then I'm going to go on. Again, today's goal is to solve the differential equation that's in the middle of the page here. That's the goal. What we're going to find, I mean, just so I'm not like keeping you in dramatic suspense or just so you see the structure, like the punchline is going to be that answer that's written on the bottom. Again, I don't expect that you would already, you might be familiar, you might have seen it, but I'm not saying it's self-evident why that is the answer. I'm just saying that that answer is an example of something that has the right form, which is plug in t, get out x. And our job today is to show why that answer is the right one. I also want to say one last thing, sorry, before I look at the chat, before I turn the page. We're trying to solve a differential equation. Again, this is not a math class. And also this doesn't assume that you've taken 85 million math classes. If this were a math class, if this were a study of differential equations, we would do the mathematically logical or the educationally logical or reasonable thing, and we would start with differential equations that centered around first derivatives. We would start, in other words, with differential equations that are known as first order. It would be totally reasonable to assume that they would be simpler to navigate or more clear to navigate than differential equations that are based around a second derivative. The differential equation we have here is focused on a second derivative. It says that the second derivative of x with respect to t is some function of x, okay? I want to make it clear again, we are skipping, in effect, straight to second order differential equations because that's where the physics is bringing us. The physics, like the natural world is not here to educate us about math. The natural world just presents itself, and then we come up with math or we discover math in order to make sense out of it. When we look at the natural world, specifically the world of motion through space and time, we more frequently slam into second order differential equations. We more frequently just like encounter second order differential equations than we do first order differential equations, for the straightforward reason that F net equals NA, that force, net force, is associated with acceleration, the second derivative of position with respect to time. That is, what we feel in nature is not motions, but changes in motions. So nature is just asking us to get ourselves together and start dealing with second order differential equations. That's what we're going to do here. We're recognizing that we've never done it before. It's not an assumption that we've done it before, but it wasn't an assumption that Newton had done it before, or Hooke, or anything like that. It is an assumption that we can do it, and we will. All right, I'm going to turn the page. I'm also going to look at the chat. Sorry. Okay. Sorry, I'm just looking at the direct chat.
Watch the songs on YouTube or whatever.
Okay.
That is what
okay.
I did. I thought.
So to turn the page, I just want, okay. So backing up a step, like again, where's this? So we're doing a math thing here. I can't deny, like what we have in front of us is a mathematical project. The mathematical project is to get a solution to d2x over dt squared equals negative k over mx. Get a solution to it, solve it. That does not mean get a number. We're trying to find a function. Also notice, I know we're used to thinking of science, maybe some of us are used to thinking of science or physics as, oh, we have a problem and then we get the correct equation and we plug into the correct equation. Like as long as we have the correct equation, we can plug in and solve the problem. But I'm saying real science, real scientific research, or real experimental physics is not about plugging into the correct equation. It's about deriving the equation for the first time. That's what physics is about. So what are we looking for here when I say we're trying to solve this differential equation? I'm saying we're looking for a function expressed directly and explicitly as a function, a dependent variable expressed as a relationship with, or the output of, some independent variable, okay? And again, the dependent variable here is x. How can I tell? Because it's in the numerator of that differential, and the independent variable is t. It's in the denominator of that differential, of that derivative, okay? So the differential equation we're trying to solve is d2x over dt squared equals negative k over mx. Where the heck did that come from? I'm saying it came from physics. What physics? Well, Newton's second law, which is like always true in classical mechanics, net F equals ma, right? And Hooke's law for a spring. Like, what are we dealing with here? We're dealing with I should have drawn a diagram, totally my bad, but we've looked at the diagram now 100,000 times. We're looking at a mass on a horizontal spring. The only force acting on the mass is the elastic spring force, Hooke's law, negative kx. And Newton says that the sum of all forces acting on an object produces the acceleration of that object. So basically I'm saying, I mean, we did this last time, but just to say the physics is saying, whoa, hello, sorry. The physics is saying, right, so the physics is saying this. So then we just rearrange it to find the differential equation, and we're looking for x as a function of t, right? Okay. Now, so we're almost up to where we were right at the end of last class, but that's like our goal here. Again, just a simple system of something going back and forth, oscillating in a conservative, continuous, patterned way, something oscillating on an optimally elastic spring is what's presenting us with this equation in this situation. We want to know, so what we know is that the rate of change of position with respect to time is somehow linearly dependent on position itself, right? If it were just dependent on time, no major issue. But the rate of change of position with respect to time is dependent on not time, but on position itself. It's that circular feedback like phenomenon that makes this a differential equation. Now we want x as a function of t. What do we do? We conjecture. Okay, there's no algorithmic direct closed form procedure for, you can't just like do some algebra or just like unpack this thing and just get an answer. We actually, whether we're mathematicians or physicists, whether we're 21st century people or 17th century people, we actually have to think out of the box and sort of retrofit this, really, retro engineer it. And again, by the way, even if we were super advanced in math, that would just mean that we're so used to this, we've done it so many times, that we kind of already have like a intuitive sense or experience-based sense of what the conjecture should be. But no matter who we are, we have to conjecture a possible answer to this and then see if it works. That is our method. We are going to conjecture and verify, i.e. guess and check. Now, where do we get the conjecture? Well, good news is we're scientists. So we've actually collected data in a lab, or at worst, we've pictured what would happen if we collected data in a lab. And what do I mean by data? I mean X versus T data. I mean, like, and obviously stop me if you want me to go back at any time. I mean, in fact, oops. Yeah, sorry. Okay, it could be worse, right? Yes, especially power tuning, it could definitely be worse. I mean, if we picture time, hello, sorry. If we picture time on the x-axis, on the independent variable axis with t, right? And we picture, so in other words, t, and we picture x position as the dependent variable on the vertical axis, right? And we picture a mass going back and forth along an x-axis of space, right? And if we picture that the equilibrium position, the middle position, is what we know as position 0, and if we picture that this mass did not start at 0, right? It was not originally held at 0. First of all, the problem told us that it was originally held at some initial position x0, which happened to be 15 centimeters to the right of 0. First of all, the problem told us that. Second of all, if we really think it through, if we understand anything about equilibrium, we realize that mass better have been let go initially from some non-equilibrium spot, because if it were let go from the equilibrium spot, nothing would ever happen to it. It would just sit there, right? So the mass started somewhere like on the positive side of 0, somewhere that we're calling the initial position x0. And it started coming in towards 0, then it passed 0 and kept going. And then it turned around and came back to 0, past 0, kept going, then it turned around, right? I mean, it's going horizontally, but we're graphing horizontal positions on the vertical axis of a graph. We're putting space, one dimension of space, on the vertical axis because it's depending on the one dimension of time that's on the horizontal axis, right? So if we picture if we imagine ourselves like measuring where this mass is every single millisecond, or so, at equal time intervals, every single millisecond, every single centisecond, whatever, every single second. If we picture what kind of numerical space markings we would get, if we picture a table of values, in other words, and the thing started at x0 and then went to 0 and then went to negative positions and kept going, right? Oh God, I'm sorry. I shouldn't have. Zero, 1, 2, 3, 5, in any units, right? 1 millisecond, 1 centisecond, whatever. But if the initial position was, all right, in this case was 0.15 meters, and then 1 second later, it's a little bit closer to, say, 0.14 meter. I'm just making up sort of arbitrary, but right, and it goes down and down until some amount of time when it's at 0, and then it goes to negative 0.113 and negative, right? I mean, we can picture that this is the data that we would collect if we had a pretty good mass on a pretty good spring going back and forth, or we actually did the lab and we got this data, if this thing is going back and forth and back and forth, and if we assume it's going back and forth somewhat smoothly, like this is nature, this is the real world, this isn't a cartoon. If we assume that this thing can't like stop instantaneously and turn around, it takes some time to slow down and stop and to speed up. If we assume that everything, in other words, is continuous and smooth, I think we would picture something like this. And I think this is what we said last time, right? Like some sort of sinusoidal or cosinusoidal function, but or at least that's the simplest possible realistic thing I could imagine this being. Maybe it's more complicated, but that's the simplest possible relationship I could imagine collecting from this data in the lab. And note that I think it is a cosine. Now, this is a minor point perhaps, but I do think it's a cosine, not a sine, because I don't think it's starting at the origin, because I think if we put the mass originally at equilibrium, it wouldn't go anywhere, right? So as scientists, we conjecture that the lab data would look something like this. That proves nothing. It's just giving us a starting point with which to work. So last time we said, based on this data, we would then based on this, we would conjecture and again, please notice, I mean, you've done various different labs in lab, and I know your very first lab was with a mass on a spring, but you took various different types of data, but like there's all different kinds of data one could take. I'm talking about if you took a spring and let the position of that spring vary as a function of time. Like, yeah, as opposed to certain things, as opposed to other relationships you could look at, such as how does the period of oscillation relate to mass or something, which is also interesting and we're going to get into, and you didn't have it, but that's a different relationship, right? If you did this relationship, which is what we're looking for, the XT relationship, and now all that talk later, and I'm just now right at the point that I feel we ended at last time, for good or for bad. This is sort of where we ended last time, that I conjecture that X is some sort of cosine function of T. Now I say some sort of, I put blanks before the T and before the cosine. I said this last time. I have to put blanks as a scientist. I'm building a conjecture here, or I'm building a relationship. I'm first starting with its basic shape, the basic type of dependency, form of dependency. I think it's a cosinusoidal dependency, as opposed to, for example, I don't think that X relates to T. I don't think X is a function of T squared. Like we already said, I don't think it's a function of T cubed. I don't think it's a parabola. I don't think it's a cubic. I think it's like a back and forth curvy thing like cosine. But I don't just write down X equals cosine of T. I don't do that because because of units, basically. You can't take, I mean, T is measured in seconds. These are measurements. This is data from the real world. T is measured in seconds. You can't take the cosine of a second. You can take the cosine maybe of a degree, but the degrees are a little bit unsophisticated and a little bit indirect and less helpful to us than radians, which is the most direct unit upon which you can perform trigonometric functions, right? So in other words, I think right? The first thing I'm saying is that there's got to be a constant right before that T. It's got to be measured in radians per second, because radians per second times seconds will cancel out the seconds and leave us with radians. Like literally, like that is a scientific way of thinking. That has to be the case. It doesn't, again, this doesn't prove anything yet. But what I'm saying, it's all if thens. It's all about consistency. I'm saying if we're going to take the cosine of time, then we better take the cosine of something times time. Like if the cosine is correct, then there's got to be something right before the time that works the units out correctly, right? And similarly, right here, this is a little bit of a funky point. It can get a little bit dicey, but once you take the cosine of something, what you get is a unitless or dimensionless output, right? Like the cosine of pi over 2. I almost want to stop and ask people, but I'll be very impressed. I'm not going to stop. I'm just going to slow down. If anybody wants to put in the chat, if anybody's still with me, the cosine of, for example, pi over 2 radians. Does anybody want the cosine? Actually, that's kind of an obnoxious one in a way for this purpose. Let's say, what's the cosine of pi radians? Anybody want to put in the chat? I won't make a big deal, but anybody, the cosine, or anyone want to say it out loud, the cosine of pi radians? I'll give you a hint. That's the same thing as asking, what's the cosine of 180 degrees? Nice. Fat. Oh, I shouldn't have said. I'm sorry. I should have given other people a chance. But yes. Okay. Just in the name. Totally. She's right. She's totally right. And maybe I'm being a little totally right. That's totally awesome. And of course, she could submit that for points. I'm sorry. And what she said, and she is Sam, and what she said was -1. And that's totally true. The cosine, and that's awesome. And I'm totally psyched. I'm just mad at myself that I probably should have given other people more time to respond and stuff. But yes. Totally right, and Sam can totally submit that for points. She can submit it for right or for wrong, blah, 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 blah. But yeah, the cosine, and ultimately you all do kind of want to know your unit circle. Ultimately, you kind of, and maybe we'll go over it at some point, but you're going to kind of need it for all this. But yeah, the cosine of pi radians is the same thing as asking what's the cosine of 180 degrees. And the answer to that is -1. But here, and that was like a nice little review question, and yay, Sam. But now here's my real point in bringing it up. It's not just like to quiz people or whatever. What I want to make clear is that Sam's answer was like really, really technically correct, meaning the cosine of pi radians is not -1 radians. And she didn't say that it was. And it's not -1 meters. And it's not -1 kilograms or anything like that. It is -1, right? I mean, like the cosine of like anything is just a number ranging from -1 to 1, right? And same thing with sine. Cosine and sine return dimensionless values. Very important to recognize. And strictly speaking, they're actually, well, anyway, they're returning dimensionless values. So even after we take the cosine of radians per second times second, the seconds cancel and we get a nice cosine thing, then we're just sitting there with a number. But what this function says, or what the kind of function we're looking for says, we need something measured in meters. So we're going to have to take whatever that number is that the cosine spits out and multiply it by something that has meters in it, so that our whole answer is in meters. Okay, so right off the bat, just as scientists, as physicists, trying to play our way with a differential equation, we already know some details here. And by the way, let me say again, I know I'm super defensive on this point. I mean, for a lot of reasons, I'm defensive, like trying to be a physicist, trying to act like a mathematician, whatever. I really want everybody to understand that this process of trying to build a function like from nowhere, or to like piece it together from conjectures and stuff. Again, this is the nature of actual lab work. This is what we do as physicists, is you get a bunch of data. I mean, you take a bunch of data in order to determine a relationship. You spit the data out on a scatter plot. Then you look at the scatter plot knowing that there's no way your data is perfect or that your plot is perfect, that it's better and better if you took a lot of points, but by the nature of it being measurements, it cannot be perfect. So you look at all your data on a scatter plot and then you try to see what shape does this data seem to fall into? What mathematical relation do I know that best approximates, or in its simplest form seems to be the simplest possible way to see this data? I mean, it's called curve fitting, right? Or model devising. And then you try to, you tinker around until you have a mathematical description of the relationship that you found in the data. Like that's the point of an experiment. The result of an experiment is to get a new mathematical relation, which means you're trying to piece together a function from a graph. Like that's actually what we do. So this isn't like this to a lot of people at first, this looks like not really doing math, and we're not really doing science. It looks like we're just like farting around and like trying to convince ourselves of stuff. But that is what science is when you're actually doing it. Okay, anyway, I'm defensive about that. But so what do I have so far? What I have so far. So yeah. Okay, so now we're going to give names to these arbitrary constants, these placeholding constants. I give names. I don't mean like Fred and Yabberbaum or something. I mean like letters, right? I mean, just like X or Y, except we don't want to use X or Y, partly because we've already used X, but also X and Y and Z are generally names for variables, right? Our variables are already covered. T is the independent variable, X is the dependent variable. These things that have units, they are constants, right? I mean, i.e., they're just numbers. They are just literal numbers that aren't going to change throughout the oscillation of one system, throughout one experiment. They're not going to change. It's just that they might change from experiment to experiment. We don't literally know what literal numbers they are. So we're going to give them names, okay? And the names could be anything. They're just placeholders until we learn more about these things. But so I'm going to okay. First of all, I'm going to put something that looks like a lowercase w, but isn't. So let's get this straight right now. I know people see it all over the web. People have seen it like maybe weeks ago when you first started to do this homework. You see it all over the web. It looks like a lowercase w. It's not. It's a lowercase omega. I mean, it's the Greek letter omega. It's lowercase. We could have used anything. It looks a little intimidating or it looks special just because it's Greek. It is special, as it turns out. It does turn out to be very, very important letter in all this. But I want to make it clear again before I go any further. It's just a placeholder right now. Just because we're using a Greek letter doesn't mean that we know anything about it. In fact, we're using a new letter, because we don't know much about this thing yet. It's a lowercase omega. I mean, yes, it turns out with the benefit of hindsight, with it, there are reasons that people pick this letter as opposed to others, and we'll see those reasons too, but it doesn't matter. It could be a P, it could be a W, whatever. So it's a lowercase omega. I'm going to the next page. What do we know about this? Again, we're just establishing that we don't know anything about this lowercase omega really, except its units, right? So we know, what do we know about it? We know that the units of omega are radians per second, right? So actually, let's stop and think about that for a minute. That means just those units alone do tell us something about it. And also, if we think about it in terms of a graph, if we just think mathematically, we do know something about it. It's some kind of rate per time. It's a rate, right? Right, it's a ratio, it's a rate per time. Now it's not a velocity. Omega is not a velocity. It's not meters per second. It's not how far something's going per unit of time, but it's radians per second. Um, uh, in terms of the cosine graph, it's how many radians, how many portions of pi or 2 pi, or if you want to think in terms of degrees, how many degrees we're advancing per each unit of time. In other words, and you know from math, in a way, what omega is measuring in a way is how many humps on the cosine graph are occurring per each unit of time. Let me put it another way. Okay, I want us to, oh God, my computer may run out of batteries. That would really be terrible. Oh my God. Oh my God. Okay, I only have 10% and I'm outside. We might, wow, this would really be a disaster. If I'm not sure we're going to do it, but all right, anyway. Omega is measuring radians per second. And I know people have different fuzzy feelings about what radians are, but we do know that a radian is a unit of measurement for an angle. You might think that you prefer degrees over radians. Hopefully by the end of this course you won't, and you'll see why. But either way, whether it's radians or degrees that you think in, they're each units of measurement for an angle. So now I want to stop and ask myself, what do I actually mean by an angle? What is an angle? And like also, even more to the point, why the heck is it coming into this whole situation? Like we started with something going back and forth, back and forth, back and forth. Now we're talking in terms of cosines. Cosines, because we're looking at the graph, cosines are bringing up angles, but whoa, where are they? I mean, angles make a lot of us think about triangles. A lot of us, when we think about angles, we think about like two lines intersecting at a point. Like a 30-degree angle is like sharp sawtooth, and a 60-degree angle is like a bigger tooth. And so we might be thinking, wait, why are triangles and angles and vertices suddenly coming up in a situation where something's going back and forth and back and forth? And here's my answer to that. Good question. And it's what used to confuse me all the time. But here's why angles are coming up. I mean, yes, because the cosine is coming up, but for a deeper reason. Here's why angles are coming up. Here's what an angle is. An angle is a portion of a circle. That is the key to this whole deal. Actually, really, it's like the key to the rest of our lives when it comes to trigonometry and this stuff. An angle is not. I mean, it is the intersection of two lines, but that is not a helpful way to think about it. That's a really confusing, distracting way to think about it. What an angle is a portion of a circle. When everybody in this room, in this Zoom room, whatever, all of us know what a right angle is. Whether you call it a right angle, whether you call it a 90-degree angle, whether you call it pi over 2 radians, we all can recognize a right angle a mile away, right? It's like when the two lines, it's very hard to describe, but we know what a right angle is. It's when like a vertical line and a horizontal line meet, right? Well, think about it. It seems hard to describe until you think of angles as portions of circles. When all of us know what a right angle is, what we're really saying is all of us can recognize a fourth of a circle when we see one, right? A right angle is a fourth of a circle, like literally, literally, literally. In fact, doesn't matter how big the circle is, right? Doesn't matter how big the two lines are, whether they have a radius of 1 meter, and so they carve out an arc length of like pi over 2 meters, or whether they have a radius. In other words, well, just what I just said, an angle is a portion of a circle, and the whole idea of it is it's the portion, literally, the fraction of the circle, the piece of the circle that doesn't care how big the circle is. It's a portion of the circle in the direct sense that it is the pure ratio of arc length measured in meters divided by radius measured in meters, and the meters cancel, right? What an angle is like how much crust length you're getting per size of pizza slice. And what we're saying is like, if you double the radius of the whole pizza that you cut a slice from, then you'll double the arc length that you get no matter what, right? Like, right? If depending on how big my circle is, if I make the circle bigger and bigger, if I make the radius bigger and bigger, then a fourth of this circle will have bigger and bigger arc length. But what angle is just it's saying, okay, how much arc length would you get if we all just agreed to just look at circles of radius 1 so that we don't get distracted by the size of the radius? Angle is literally a portion of a circle. What is 180 degrees? It's half of a circle. Pi radians, half, same thing, right? In other words, and this is where the radians idea comes from. We're just saying, look, go around a whole circle. Go around a full circle. If you go around a full circle, the arc length that you'd carve out, the total amount of crust that you would get going on a full pizza would be the full circumference of that pizza, 2 pi r. Like the circumference of any circle is 2 pi times its radius, right? And if you divide that by the radius, so 2 pi r divided by r, you get 2 pi. Go around a whole circle. You can call that 360 degrees if you want, because you're used to it, but there's no actual, like, there's nothing immediately obvious corresponding to 360 when you just look at a circle. But what you're taught when you say 360, we all know you mean full circle, like if it's a snowboarder turning around or whatever. And what is that in pure units? It's 2 pi radians. What's pi radians? Half a circle. What's pi over 2 radians? A quarter of a circle, et cetera, et cetera. So what I'm saying is an angle is a portion, a pure fraction of a circle. It's a pure ratio. So technically, what I'm really saying is that technically radians are not actually a unit. They're even a placeholder name. A radian is really a pure thing. It's meter divided by a meter, which is why when you take the cosine of it or the sine of it, you get a pure thing like the number 1 or the number 1/2 sidebar, right? So in the end of the day, an angle is a portion of a circle. what I'm trying to say all right here, and again, and my battery might die, and then I'm gonna hope the board saves us, but we'll see. This is all looks like a slight side road, but I'm saying so far our function looks like something times cosine of what we're calling omega times t. Omega, we don't know anything about it except it's measured in radians per second. What the heck are radians? Ultimately, I'm saying a radian is a portion of a cycle. Radians per second is measuring the rate at which our process is cycling. A radians per second is a cycling rate. What I'm saying so far is that omega, which is only there because of units, the only thing we know about it, therefore, is units. But by knowing the units, we already know a lot. Omega is measured in radians per second. That means it's measuring a cycling rate. Omega is measuring, sure, it's measuring, if you think of it on the cosine graph, it's measuring like the number of bumps in that cosine graph per unit time. But in the physical world, in terms of our mass going back and forth on the spring, like I don't see any angles in the mass going back on the spring. I don't see radians. I don't see, but what I see is something cycling back and forth and back and forth. What omega is measuring is the number of times per unit time per second that this thing is completing a certain number of cycle portions. Like omega is not necessarily measuring full cycles per time, it's measuring cycle portions per time because an angle is a portion of a cycle. What this is literally measuring is the number of radians per cycle. So the only question sort of I have to left to answer, at least at this moment, is, well, how big a portion of a cycle is a radian, right? Like, right? And that's answerable. Yeah, sorry. What I have here at the bottom of the page is an approximation. It's not exactly true, it's approximately true. But remember, we're physicists, not mathematicians. Everything we're doing in the lab is a measurement, which is approximate anyway. And sometimes approximations are a lot more useful to our intuition than exact numbers are. What I'm saying here at the bottom, okay, I think might be very, very useful for some of you. For years and years and years, radians were totally abstract to me. I had no idea what radians were. I had to use them all the time. They always intimidated me. I sort of like just worked around them. And the minute radians were involved in anything, I was just like fuzzing out like, okay, radian. what I'm ultimately trying to say here is, you know what a radian is? You want to know what a radian is? I'll tell you what a radian is. A radian is a freaking sixth of a cycle. That's what a radian is. It's not exactly a sixth of a cycle. It's like a little bit less than that. It's not 1/6. It's 1/6.28, blah, blah. But whatever. The point is, it's a portion of a cycle. To get a feel for it, you could be exact once you have a feel for it. But to get a feel for what a radian is, it's a sixth of a cycle. Where I get a sixth from? Because 2 pi radians is 1 cycle. 2 pi radians is exactly 1 cycle. So a cycle is approximately 6.28 radians. A radian is about a sixth of a cycle. If you picture it in a circle, that means a radian is a little bit less than 60 degrees. It's a little bit less than a sixth of 360. In fact, a radian is about 57 degrees. That's all it. And what a radian is in a circle, if you think about it, is 1 radian is the angle for which the arc length equals the radius. Like if S and R are equal to each other, if S is 2 and R is 2, or if the arc length you get is the same number as the radius, then, they cancel out and you get 1, right? So what a radian is a radian is a slice of pizza whose crust is basically the same size as its edge. It's even better, and please write this down because I know I'm running out of batteries and I'm not gonna be able to write this down. If you want to picture a radian on a circle, and this is what, right? If you want to picture what a radian is, it's an angle of about 57 degrees. What's the significance of that? Is it's the slice of pie or pizza or whatever that you would cut that looks as close as it possibly can to an equilateral triangle, right? Like the crust is like a curvy version of the edge. Right? If you have a really long, thin slice, that's not a radian because the crust is a lot shorter than the radius. If you have a really, really small slice where someone's here, where the crust is like really big and the edge is really small, that's not a radian either. A radian is where the crust, is of course it's gently sloped, and that's why this is not exact. But when the crust length is precisely equal to the edge, so that the slice you have of pizza or whatever is just squat enough to basically look like the curved version of an equilateral triangle, that means you've cut the whole pie into basically 6 slices. That's the only way to do that. Like if you cut the pie into 4 slices, each one's going to be like 90 degrees, pi over 2. Totally understood. I totally get it. No problem. And so am I. God knows what's going to happen to this, but totally understood. Thank you. But I'm saying, whenever you think of angles from now on, think of them as portions of circles. A right angle, a 90-degree angle, pi over 2 angle is a fourth of a circle. A pi angle is a half a circle. A radian is essentially a sixth of a circle. And if you cut a circle, any circle, a pizza pie, if you cut a circle into 6 slices, each one of them is going to basically look like an equilateral triangle. The crust will be the same size as the edge. Cool. That's what a radian is. Now, how does this relate to masses on springs? I'm saying a radian is a sixth of a cycle. So when we measure, when we do this thing of omega equaling radians per second, we're literally measuring how many cycle sixths does this thing undergo per second. Like, in other words, if omega were 6, or exactly if omega were 2 pi, that would mean the thing is doing 1 full cycle per second. If omega is pi, right, like the number, which is basically number 3, and that means this thing would be doing 3/6 cycles per second, a half a cycle per second. A radian is a sixth of a cycle. And radians per second measures cycling rate. I want everybody to be clear on this, okay? And we know this, assuming our solution works at all, like if it has any omega in it at all, that's what omega is going to mean. We still haven't proved our solution. We haven't finished our solution, let alone proved it. But this omega that we're sticking in, we're establishing now for the first time, like it's going to come up in your homework all the time. It's all over the web. We didn't discover omega. We're sort of making it up right now, just as a placeholder. But whatever it is, omega, it's standing for cycling rate. And it's measured specifically in cycle sixths per second. I'm always going to say that. Sixth of a cycle 6. And people are going to like, where do you get 6 from? A sixth is 1/2 pi, approximately. Okay. Now, there's a name for this thing. Before I go any further, and again, I'm really worried about my battery, but before I go any further, this cycling rate has a name. It's called angular frequency, the frequency with which we complete certain amount of angles. please again, remember, what's angle got to do with anything? I mean, we're talking about a mass on a spring. It's not making angles. It's not going off on a slant or something. The angles we're talking about here are portions of cycles.